This research is SHIELD, Secure Aggregation Against Poisoning Attacks in Hierarchical Federated Learning. Let's first discuss what is federated learning. Federated learning was introduced by Google in 2016, which is a collaborative machine learning algorithm which used to train a model. The collaboration is coordinated by a federated learning server, which shares the global model to all the users, and the users train the received model using its local data and sends back to the trained model to the server. The users do not share the data outside the devices, so it's privacy preserving. And ultimately, the server aggregates all the received model from the users and distribute the aggregated update to the users again. This process happens iteratively until a certain convergence is met, and ultimately, at the end of the training, all the users will have a properly trained model. In federated learning, the intermediate nodes, such as edge nodes or core nodes, they do not perform any aggregation, they just relay the model updates towards the server. But in hierarchical federated learning, these nodes also perform model aggregations, reducing network traffic towards upper layers and effectively utilizing the computational power at intermediate layers. One security issue associated with federated learning and hierarchical federated learning is the poisoning attacks. In a poisoning attack, the users or the malicious users train the model based on malicious data, or ultimately they create a malicious model. If they train the model on malicious data, we call it's data poisoning. And if they poison the model after the training, we call it model poisoning. Ultimately, it creates a poisoned model that serves the adversary's objective. And at the inference stage, it will, for example, misclassify a certain set of inputs. The existing robust algorithms against poisoning attacks in federated learning are not suitable for hierarchical federated learning scenarios. Therefore, we designed a novel robust algorithm called SHIELD, specifically designed against poisoning attacks in hierarchical federated learning. As in federated learning, the central server transmits the global model to each client, and the clients train the global model using their local datasets and transmit back to the intermediate layer. Now, in federated learning, the nodes in this layer would forward the model updates to the central server, but in this case, now the intermediate aggregation happens. During the intermediate aggregation, our robust algorithm performs a clustering using HDBSCAN clustering, outlier removal, and cluster averaging, and only the cluster average will be forwarded to the uh, next upper layer, and this happens for all the intermediate layers. Once the cluster averages are received towards central server, the central server also performs HGB scan clustering, outlier removal, and cluster aggregation, cluster averaging at the central server, and then picks the best cluster as the next cluster average to proceed with the training. This way, all the poisoning effect will be removed. To illustrate our solution, we designed a hierarchical federated learning network with 4 layers, where the central server connects to 5 nodes, and those 5 nodes will be connected to 25 nodes and ultimately to 250 devices. We use 4 datasets called MNIST, CIFAR10, KDD CUP99, and 5G NIDD. 5G NIDD is a dataset developed at University of Oulu using its own 5G network. We use TensorFlow with Keras to simulate our scenarios, and we use targeted poisoning attacks, single and multiple label flipping, and untargeted poisoning attacks, random label flipping, random label swapping, sign flipping, same value and gradient ascent attack. To visualize our results, we created the simulation, and uh, when we execute the simulation with a certain configuration, we can see how many clusters were created at each layer, at each node, and what is the selected cluster to proceed with the next iteration. Ultimately, when the training ends, we can see how many examples were properly classified and what is the backdoor accuracy and the main task accuracy. Backdoor accuracy is the accuracy of the poisoning task, And the main task accuracy is the accuracy of the task that is not concerned by the poisoner. This screen shows our dashboard created by React to showcase the results. You can see in the benign scenario, all the classes have proper accuracy and the model is properly trained. And in the poisoning scenario, we can see we there are different instances where we have 20% poisoning, 40% poisoning, and 60% poisoning. In 20% poisoning, we can see the class 1 is somewhat affected, and in 40% poisoning, the class 1 is severely affected, and in 60% also, the class 1 is severely affected because the objective of our poisoning is to reduce the accuracy of class 1. In this screen, you can compare different scenarios. For example, if we get the same accuracy as the benign system with the defense implemented. We first compare the benign scenario with benign plus defense, which is shield. So we can see that the system recovers the to the original scenario with the shield. And also we can compare when there is poisoning and with shield. We can see that when 60% is poison, class 1 is severely affected, and with the poison plus shield, the class 1 is restored. As the key results of our research, we can present for different poisoner configurations like random, biased, and distributed, and for different poisoner percentages, we can see that the solution recovers the system to the benign state for each poisoner configuration and percentage. We also compare our results to the state-of-the-art algorithms for targeted poisoning attacks and untargeted poisoning attacks. The results show that it's either perform better or it's either achieve comparable accuracy with the state-of-the-art algorithms. That's all for this research. If you have any questions, you can reach me via this email.